So this session is about using disk drives. And of course, I'm from Seagate where we make disk drives. And I thought about, well, what do we do to most effectively let people use drives? Well, of course, the most effective thing we do is put them in cardboard boxes and ship them. But I don't know, you maybe be, whoa. You might be just waiting on the edge of your chair to hear a talk about packaging and shipping disk drives, but I would fall asleep if I tried to give it. So I thought, well, now I can talk about anything I want. So as opposed to Carol talking about the past, I'm going to talk about the future and where I think some aspects of hard drive archives might go. And specifically, I'm going to talk about where topology might go, where capacity might go, and where intelligence might go. And there could be a lot more topics that might be just as interesting, but these are the ones I wanted to talk about, so that's what you get. So today's architectures center around directly attached hard drives. Almost 90%, I suppose, are SATA drives attached directly to a motherboard, and basically an architecture that's not much more complex than a PC. And you can see this CSP architecture cartoon I have shows the storage servers down at the bottom of the Ethernet network where there's a server and a bunch of drives directly attached. Okay, well this is pretty simple. You know, most junior high school kids know enough about computers to be able to build or maintain one of these. And you have this mother hen sort of server sitting over, hovering over all these drives and able to do all the management functions. That makes it a really simple model for maintaining these drives. But there's some disadvantage, right? You're paying for those CPUs. There's a fundamental inflexibility in the relationship between number of drives and processors. I've had customers complain about this being a real issue. And finally, because they're converged, you have processors and drives, same cabinet, there's probably probably not as efficient a system for cooling as you would like. Well, one of the things several companies have talked about is the idea of network storage, where you get rid of the storage servers and you have all these drives directly attached to a network, such as Ethernet in this case. And there are some obvious advantages, right? So, no servers. You actually have some more redundancy freedom. Where you have a sea of disk drives like this, you can use parity techniques that wouldn't be quite as simple because you could have them amortized across all these drives. Something like the NAND parts shown this morning. It simplifies the software stack. If for no other reason you have that, you've taken out that intermediate layer with the storage server, and so perhaps you have lower latency. But there are some real disadvantages. Right? Management practice is not really developed, right? If those storage servers are gone, well, where are you going to manage these drives? Who's going to pay attention to if a drive fails, for instance? Who's going to rebuild it or replicate it, as the case may be? The software stack isn't really ready for it yet. One of the big things you'd really like to do with something like this is to be able to have networked solid-state storage for low latency, shared access by all the application servers. But if you put solid-state storage at the end of an Ethernet network, you know, it's not a good match because the network has so much latency. So, what about the networking part of network storage? What can we do to fix this? Well, today, and now I'm using the NVMe standard proposal as a basis, there's three choices being considered: Ethernet, InfiniBand, and Fiber Channel. Right? Well, Ethernet's ubiquitous, it's really cheap, it's fast in the sense of high bandwidth, but it's basically software interpreted, and so there's a lot of latency associated with breaking down Ethernet frames. And it's not deterministic the way, say, Fiber Channel or InfiniBand can be, so you have the danger of dropped frames, which is really bad for storage latency. InfiniBand, on the other hand, a lot faster, a lot more complex, but it's not nearly as widely deployed, and it's not an HDD interface today. Fiber Channel, I'm not going to talk too much about. They basically used to be a drive interface, but it's not any longer. I think it was at 8 gigabit, they dropped the electronic interface definition, so it's really only used for storage area networks today. And storage area networks don't seem to be a big part of archives. So what do we need? Well, we need a low latency network so that we can enjoy the advantage of putting solid state or high access performance storage at the end of the network so it can be shared by any application server. And then we need some way to attach the drives. Well, here's a real problem. We heard about this a little bit this morning. PCIe is a disaster in this kind of an environment. It just doesn't scale. You can only go, I don't know, about 9 inches on PCIe. And if you wanted to lay out a 100-drive backplane, you'd have repeaters all over the place and basically have a design that would be in danger of the backplane failing, which of course is a real crisis in terms of shared storage. And so what's really needed is a low latency network that would support 2 link types, both optical and electronic, and 2 protocol modes, both blocks and objects. Now, if you try to map existing interfaces to this, the one interface that fits all cases is Ethernet, but it has those performance characteristics. You could look at SAS, right, which does optical and electronic and blocks, but no object support. So something is needed here. And if you think about something like Intel's silicon photonics, that would be almost perfect, except they haven't solved the last mile problem, right? So if you have silicon photonics coming into a backplane of drives, how do you get that from the backplane disseminated to all the drives? Not a good answer for that at this point. But this is worth thinking about. You could look at Intel's disaggregated architecture visions. You could look at HP's The Machine story. They talk about architectures like this. But the really interesting one, if you want to do some homework on this, is University of California, Berkeley's Firebox concept. It develops in a way that brings out some really intriguing possibilities with this architecture. So with that, I'll go on to the next topic, which is where might capacity of drives go? Well, the first thing you think about when you talk about capacity is areal density. That is increasing the capacity per platter. But I'm not going to talk about that. And the reason I'm not is that I'm going to talk about it tomorrow. So if you're interested in hearing about it, well, you have something to live for now because it'll be on the agenda tomorrow. But what I am going to talk about is other ways of getting more capacity. Eric Brewer's talk at FAST this February brought out this idea, well, let's change the form factor. Well, we've had lots of form factors in the past, right? Everything from really big drives to really small drives. Why couldn't we use one of those? Well, we'll talk about that. And of course, one of the things that's been done to make this more possible is to introduce helium into the drives, replacing air, and that's enabled us to put more platters in a drive. But we've kind of gotten to the limit of that. You can maybe get 1 or 2 more platters in some of the form factors, but not a lot more. It's both brought us more capacity in terms of more platters and also better areal density because less vibration means you can have higher tracks per inch. But what about using a different form factor? Now, I hope you'll let me make 2 quick assumptions. We can dispense with everything under 2.5, right? If you want to build high-capacity archives, you're not going to do it with 1.8-inch drives. Probably not even 2.5. And we can probably get rid of everything above 5.25. Unless there's somebody in the room that would really like to have a 170-pound drive and an AC motor on every drive, we're just not going to talk about those. Well, what about 5.25? I mean, it's a lot bigger. You have a lot more areal density. You could, in theory, get a lot more capacity. But just because you built it in the past doesn't mean you can build it in the future. And here's what I mean by that. To build a drive, you have to have some components. Now, most hard drive manufacturers are fully integrated, right? They sputter their own media, they develop their own heads, and so forth. But there are underlying components that suppliers have to produce. So one is a spindle motor, right? There hasn't been a 5.25-inch spindle motor for, I don't know, 13 years. And there are only 2 companies in the world that produce spindle motors, the kind of motors that have to be that you need to use in drives. They have tremendously low tolerances for vibration and so forth. But suppose you found somebody to build a spindle motor. So Joe's Auto Body and Spindle Motor Shop down in Palo Alto said, yeah, we'll build them for you. We'll produce 1 million a month. Right, okay, so you have a spindle motor now. Then you have to get media. Well, vendors, hard drive manufacturers, sputter their own media, but they don't make the substrates. So you have to find somebody that makes the substrates. Well, there isn't anybody that makes 5 1/4 inch substrates anymore, glass or aluminum. But just suppose, right? When I was a kid, we used to say, let's play like we're cowboys and Indians, right? Well, we're going to play like we can get media too. Now you run into the problem. You get the media, you get the spindle motors, now you start putting things together. But what you get is just a substrate, and it has to be sputtered with all sorts of layers of stuff, right? There's a smoothing layer, then there's a magnetic layer, then there's an attachment layer, then there's a magnetic layer, then there's an overcoat, then there's a lube. And that's all done in hugely expensive sputtering machines. Well, guess what? All the hard drive manufacturers have gotten rid of their 5 1/4 inch sputtering machines years ago. And it would be a tremendous capital expense to reacquire those or redevelop them and sputter 5 1/4 inch media for the small areal density or dollar per gigabyte gain you'd get. So it doesn't make much sense to go back to a different form factor in terms of media size. It would just be too expensive. But there is a form factor that makes sense, right? Today, the world is dominated by 3.5 inch diameter, 1 inch high drives. But we used to have a 1.6 inch high, right? So the same media size, spindle motors that aren't that far off from what we use today, but could hold a lot more platters. And so if you want to build a higher capacity drive by putting more platters together, it would probably have to be the same basic form factor, but a higher stack. And 1.6 is something we have experience for. You could do other things, but that would be the easiest to do. So that's what I call the form factor. Not as encouraging as you might think it would be as far as increasing capacity. I have one more topic. This is my favorite one. So where will intelligence go in the future, or where might it go? Well, to that, I'm going to go back to the past and look at something that was done actually first in 1979 by ICL. Anybody ever heard of CAFS? Want to really impress people? Trivia? Yeah. Content Addressable File System. ICL sold a database machine and they wanted to accelerate it, so they actually put boards on every SCSI bus that would help process the Oracle or, I can't remember what the other day, they supported 2 databases. But much later, in 1998 to 2000, there were 3 PhD theses written on what was called active disk. An active disk is really simple. You have an application running in a host, and you provide a complement to that by putting some application function down the drive to help pre-process the data and accelerate the application. Well, why would you want to look at this today? There's 3, I think, important reasons. One is the tremendous movement from structured data to unstructured data. As I'm sure you all have heard, there's a tremendous body of unstructured data that needs to be processed today. And that's exactly the kind of thing that lends itself to this concept called active disks. Not only are they unstructured, but they're massive. But maybe the most interesting aspect of this is the movement to storage objects. So that now that interface going to those drives or those storage servers isn't a block interface, but an object interface. And so now there is coinciding with the media enough semantic information so that the drive could do something intelligent on the data as required. How might this work? Let me give you a quick example. So we've got in this, down at the bottom cartoon, I think 36 disk drives. And let's just imagine, as a theoretical case, that we have the VA patient data. And the Veterans Administration has about 3 billion records. And imagine a veteran comes in and he has some unusual problem, some symptom that they've never seen before. And VA is concerned, right? Who else might have this? And so what they'll want to do is search through that data and find maybe everybody that was in the same unit at the same time, right, in the same location. Well, VA data isn't structured, right? It's just big sequential data. So what you have to do is start at record 1 on disk 1 and just start reading until you've read all 36 drives and found the records that have this unit, this time, and this location. Okay, and so that's going to take a really long time. Well, you can speed it up, right? Go from whatever hard drive you're using to a faster hard drive, and you'll reduce the amount of I/O time. And that's still not fast enough. So go to an SSD and reduce it even more to a point where the I/O time is relatively small. But notice you have not changed at all the time the application takes to process. Well, now suppose you could change that read and enhance it by invoking an applet that this active disk architecture calls for, so that when you do that read on each of the drives, and you can disseminate this applet to all the drives in parallel, and you can do all the reads in parallel, and this is how it works. You read all the data, but only give me the ones that have this unit number and this year in it, right? So now, instead of coming to the host all 3 billion records, you're going to get 3,000 records, and you've reduced the amount of data that flows into the host and that has to be processed by the application to an infinitesimal fraction of what would have to otherwise be processed by the host. That's the idea behind active disks. It parallelizes the initial analysis of data so that all drives can do it in parallel, right? It dramatically reduces the transfer of data over the network to the host, and I think that's the primary benefit model, right? Dramatically reducing the amount of data that comes into the host, and then thereby reducing the application runtime. And notice the implication of this, right? If you have some data and you want it to go faster, you just spread it across more drives. So you can actually scale the processing with the data size if you just add more drives. And I think the implication is it could impel wide declustering of data. Now, just recalling the 3 papers that were done 17, 18 years ago, they showed some pretty dramatic results. This is the paper by Archaya, but there's one by Eric Riddell and Kim Keaton as well. And what was really interesting about this particular paper, he tried it with 4 active disks, and then he tried it with 32 active disks. And notice the dramatic reduction as you spread the problem over more drives. That's exactly the implication that holds such promise for this massive unstructured data that we're looking to process. I think a really interesting concept. So, in summary, right, converged technologies where you have processing power and storage combined in one is the dominant topology. There's strong interest in network storage, but there's some problems that have to be solved, but some new architectures that could be derived from that if we can solve them. New form factors are expensive. Choosing one cannot be done lightly. It's going to be a big investment and have to demonstrate a promising return. And finally, and I think most intriguing, large archive-focused innovation looms over the horizon. And I can't wait to see it. Thank you.